Let's look at a type of chemical bond in which electrons are not given up or taken. So let's look at hydrogen. Hydrogen has one proton and one electron. So in order to fill its outer shell, it wants another electron. Well, let's say we have another hydrogen atom over here. Well, it wants the same thing. It wants another electron. Because each of these hydrogen atoms has one space to fill within their outer shell. So from this point on, I'm just going to start abbreviating atoms. For example, hydrogen, I'll just put H here, representing hydrogen. Here we'll have its outer shell with an electron in it. This hydrogen also has an outer shell with an electron in it. And what they will do is these two atoms can share electrons. So we can take both of these atoms of hydrogen and they can get together, share their electrons. So now that each of them has a full outer shell or a full valence shell. So in essence, they have merged their valence shells, and hence the term covalent. Now, in order to make this simpler and not have to write out all of these dots, we can abbreviate this with a single line. So we can denote a covalent bond by a line. So here we have, and I guess I should make this a little bit bigger. Here we have two atoms of hydrogen joined by a single covalent bond. And in fact, hydrogen goes around in nature 2 by 2. We call this diatomic because we always find that hydrogen has two atoms and it actually forms a molecule. So now I'll go ahead and define what a molecule is. A molecule is two or more atoms that are bonded covalently. So they have to have a covalent bond. They have to share electrons. Interestingly, compounds differ from molecules in that molecules have to be covalently bonded. They can be two or more atoms, but they could be two or more of the same atoms. So for example, our hydrogen example here is two or more atoms, but they are the same. So it cannot be a compound. A compound must have two or more atoms of a different type. So that is an important distinction, and I thought I would go ahead and make it here. So now let's look at some other examples. What happens if we have, say, oxygen? Oxygen has 8 protons, which I'll just abbreviate like this. It has, therefore, 8 electrons. And so the inner shell has 2, and the outer shell is going to have 6 electrons. And that means we have 2 spaces that need to be filled because we want to fill the second shell with 8 electrons. So when we fill the second and third shells, we know they want 8 electrons. We call this the octet rule, and that is simply making sure that we have 8 electrons in the outer shell. So let's take another atom of oxygen here. And again, it has the same configuration, 6 electrons in the outer shell. Again, each one of these oxygen atoms wants 8 electrons. So what can they do? They could share 2 electrons each. So in that case, they could share what we call 2 pairs of electrons. Their outer valence shells will merge. Hence, once again, the term covalent. And now we have atoms that are covalently bonded with a double covalent bond, because we're not just sharing one pair of electrons the way we did with hydrogen, where we had each hydrogen giving or contributing 1 electron to the pair, but now we're sharing 2 electrons from each atom. So in this case, with our hydrogen, we had our single covalent bond. With our oxygen, we have a double covalent bond. And we can abbreviate that with 2 lines. So instead of writing out the configuration of the entire molecule, I'll simply just write two O's for oxygen with two lines between them, and that signifies a double bond. So once again in nature, oxygen is what we call diatomic. It goes 2 by 2. Now as a final example of a diatomic element, let's look at nitrogen. Nitrogen has 7 protons and therefore 7 electrons. So the first 2 electrons fill the inner shell, and then we have 5 electrons that occupy the second shell. So that leaves us 3 spaces. So each one of these nitrogen atoms wants to fill the outer shell with 3 more electrons. So each nitrogen atom can contribute 3 electrons, and we can form 3 pairs of electrons, where each of these electrons, we can rearrange them like this, and we can have a sharing of 3 pairs of electrons, and that thus forms a triple covalent bond, so that we can abbreviate that as 2 nitrogens with 3 lines between them. So basically, a covalent bond is simply sharing of a pair of electrons in which each atom contributes 1 electron in the pair. So for example, in hydrogen, we saw the hydrogen atoms contributed 1 electron each to form a single covalent bond. Oxygen contributed 2 electrons each, 1 for each pair, so that we ended up forming a double covalent bond. And nitrogen, each nitrogen contributes 3 electrons, 1 for each pair between them, that forms a triple covalent bond. Next, let's talk about 2 fundamental elements in organic chemistry. And these are very important in biology because they're the basis of life. And that is carbon and hydrogen. So all organic molecules must contain carbon and hydrogen. Now they can have other atoms as well. They can have atoms of oxygen or phosphorus or sulfur. But in order to be an organic molecule, they have to have carbon and hydrogen as their base. So that basically, when we look at organic molecules, we'll see that they usually contain a core of carbon with some hydrogens attached to it. So this would be a short organic molecule. And we could have other things attached to it, but so long as we have this carbon backbone with hydrogen attached, then we can call it an organic molecule. So now let's look at carbon itself. Carbon has 6 protons and therefore 6 electrons. And we can denote that. We can go back to our spherical model here, and we would see that we have 2 electrons in the inner shell and 4 electrons in the outer shell. And one thing that we will notice is that carbon always makes 4 covalent bonds. One of the simplest molecules that we could make is if we had a covalent bond, this carbon bonding covalently with 4 hydrogens. And so we would get something that looks like this. And we notice that each constituent in this molecule has satisfied the need to fill its outer shell. So hydrogen over here has 2 electrons in its outer shell because it's sharing an electron with carbon. And carbon has 8 electrons in its outer shell because it's sharing an electron with each of these 4 hydrogens. So we now have a molecule called methane. This is one of the simplest molecules that we can make. And we can abbreviate it like this, where we have a carbon with 4 hydrogens attached. Now, carbon must always make 4 covalent bonds, but they don't always have to be single covalent bonds. We could, for example, have a carbon that has a double covalent bond with another carbon. And then instead of putting 4 hydrogens, we would put 2 hydrogens on each carbon. And this is ethylene. So now we have a double bonded carbon on each side, and each carbon is also bonded to 2 hydrogens. So we've got 1, 2, 3, 4 covalent bonds for each carbon. Now, let's look at another arrangement we could have. We could have a carbon that is triple bonded to another carbon and also bonded to another hydrogen. So this would be acetylene, and either way, you can count 4 covalent bonds, a triple bond and a single covalent bond. So carbon always makes 4 covalent bonds. And when it makes covalent bonds with hydrogen, it always shares the electrons equally. Now this is important because we have 2 types of covalent bonds. We have nonpolar covalent bonds and polar covalent bonds. So nonpolar covalent bonds is where we have an equal sharing of electrons between the constituents of the molecule. So each atom will share the electrons equally. In this case, we have 4 nonpolar covalent bonds when we make methane. And so there's no particular tug in any direction of electrons. All the forces on this thing are pretty equal. Now let's look at water. Water's a bit different. So when we combine oxygen with hydrogen to form water, remember oxygen has 8 electrons, so 6 in the outer shell, and it will share an electron with hydrogen to form 2 covalent bonds with a hydrogen each. But we see that oxygen likes to pull hydrogen's electrons closer to it. So what happens is hydrogen's electrons, each of the hydrogen's electrons, tend to stick around oxygen more than they do hydrogen. And so that makes this end of the molecule a little bit more negative. So the oxygen end of the molecule develops a partial negative charge. And since it's holding on to 2 of hydrogen's electrons, it makes it's got a partial charge that is equal to 2 of these hydrogen electrons that are being pulled toward oxygen. By the same token, each of the hydrogen atoms over here, or the hydrogen constituents of the molecule, are going to develop a slightly positive charge. And we denote this slight charge as this delta. So delta positive means we've got slightly positive charge over here, delta negative, slightly negative charge over here. And what that means is now the molecule is polar. It has a positive end and a negative end. So on the oxygen end is the negative end, and the hydrogen end is the positive end. And so what we will find when we look at polar molecules is that they tend to like water. And we'll see why in just a moment. So things like methane, things that are mostly carbon and hydrogen, don't like water. And the reason is that these are nonpolar covalent molecules, whereas water is a polar covalent molecule. So water has a dipole or a slight charge. So it's negatively charged at one end of the molecule and positively charged at the other end of the molecule. Now this example of water, we can also rewrite it very simply so that the oxygen makes 2 covalent bonds with 1 hydrogen each. And we can write oxygen like this, and we can write hydrogen like this. And we can see that the oxygen forms 1 covalent bond with hydrogen, another covalent bond with hydrogen. And if we draw a bunch of these things, we will see that we've got negatively charged oxygen, positively charged hydrogen, and that means that the hydrogen atoms of one water molecule might have a slight attraction to the oxygen atoms of another water molecule. So we get this kind of arrangement. Where since we have a dipolar molecule and we've got, I'll just use purple here, we have a positive dipole, so we've got negative on this end, positive on this end, negative on this end, positive on this end. We can see once again where opposites attract. And so while these are not true chemical bonds, these hydrogen bonds are not true chemical bonds, they're just simply attractions. And we can think of them kind of like Velcro. So all this is supposed to be positive. And I wrote that backwards, but in any case, we see the negative ends of the molecules tend to orient to the positive ends of the other molecules. And this is one reason why water has some of the properties that it does. It has several properties we'll discuss later, but we see that it has sort of an attraction. The molecules of water have very slight attractions for other molecules of water via the fact that it's polar, and the positive end of water of one molecule will form these very weak bonds, hydrogen bonds, with the negative end of another water molecule. Now, to give a little bit of an example of how hydrogen bonding works, we can think of it as a very, very weak connection, not really even a true chemical bond, that is not dissimilar to what we see with Velcro. So Velcro, we have little hooks and eyelets, and we can think of the fuzzy part of Velcro maybe being the negative end, and the sticky part of Velcro being the positive end. But each little tiny hook and eyelet is a very weak bond. However, if you have lots of these things, and I will say this vest is 20 pounds. If you have lots of these things, that's a pretty strong bond to be able to hold that. But if you had just one or two little hooks or eyelets, it would not be able to hold the weight of this vest. Likewise, if you have lots of hydrogen bonds occurring, then you have strength in numbers. And so this is one of the reasons that water takes so much energy to boil and make these molecules that are typically in the liquid state boil off and become in the gaseous state.